everybody. So today we're going to be looking at ionic bonding. We're moving on from electrons to bonding, and we're going to start with ionic bonding specifically because we just ended with the cations in our flame test lab. So it kind of transitions in very well to ionic bonding. Now, in case we've forgotten what ions are atoms, or we'll see today, groups of atoms that either have a positive or a negative charge. They have a positive charge if they've lost electrons, right, because they've lost negative charges. They have a negative charge if they've gained those negative charges, or they've gained those electrons. And we know, or we've seen, that they're going to gain or lose electrons and become ions in order to have a noble gas configuration. So remember that they're going to have a configuration when they're ions of these noble gases over here on the right side of the table, okay, group 18. Now, we know that ionic bonds happen between cations and anions. We've seen cations from that flame test lab, and remember that they are positively charged ions that have lost electrons. They become positively charged because they lost those electrons. And when we go to talk about them, we want to make sure that we're using accurate language to talk about the ions. Na is sodium. Na plus is the sodium ion. Easy enough. Ba2 plus, barium, but Ba2 plus is the barium ion. When we look over there at those anions are negatively charged ions. So these are the opposite of cations. They're negatively charged because they've gained electrons. And when we go to name these, it's a little different than naming cations because we change the ending. We use the elemental name of the atom, and we change the ending to "ide." So instead of bromine, this is Br minus, so it's bromide, changing the ending to "ide," ion. Instead of oxygen, O2 minus is oxide, ion. So a little different than cations, slightly more complicated with naming, but not much. Now, we see that ionic bonds, yes, they happen between cations and anions. That cation is typically a metal, the anion, non-metal. So an ionic bond is also between a metal and a non-metal. We haven't had a chance to talk about properties of metals and nonmetals, so we'll take a look at that right now. Metals are those on the left of this stair-step line on the periodic table. So if I'm drawing that stair-step line, remember that stair-step line comes right down there. So metals are everything on this side of the periodic table, whereas nonmetals are everything to the right of that stair-step line. Metals are good conductors of electricity, which you can guess because of things like copper for copper wire, or tin or aluminum, things that we use for cooking. Nonmetals, however, are poor conductors of electricity. Metals are solids at room temperature typically. So if you see the elemental form of any of these, typically they are solids, whereas our nonmetals are typically, not always, but typically gases. The exception for our metals is that mercury right here, even though it's a metal, it's actually a liquid at room temperature. And bromine, even though it's a nonmetal, it's not a gas, it's actually a liquid at room temperature. And carbon, phosphorus, sulfur, selenium, and iodine are solids at room temperature. So there's a lot more exceptions in the nonmetals, but other than that, they are gases. And other properties of metals, we see that they're shiny. They are malleable, which means they can be reformed into sheets without breaking, like pounded down into sheets without breaking. And they're ductile, which means they can be rolled into wires without breaking. Other properties of nonmetals is that they're dull. They're not shiny. Those that are not gases, obviously. All right, so now that we're pretty clear on ionic bonding and just general what ionic bonds happen between, we want to take a look at the big idea with ionic compounds. So the big idea, let me go this way actually, so you can see the board better. The big idea is that ionic compounds are held together by chemical bonds. So we're going to talk about chemical bonds in a second, but these are bonds formed by the attraction of oppositely charged particles. That's why it happens between a metal or nonmetal, a cation and an anion, because you have a positive attracting a negative and vice versa. So it has to be those oppositely charged particles. Now, some definitions we want to be aware of moving forward is the chemical bond that we mentioned up here. Chemical bonds are just the forces that hold two or more atoms together. It's just what keeps them together instead of splitting apart. The octet rule is really going to be what we see with any kind of bond that forms and why that bond forms. So atoms are going to transfer or share electrons. Today, we're talking about the transfer of electrons because that's an ionic bond. Sharing of electrons is going to be a covalent bond, and we'll talk about that later. And they're going to do that to achieve the noble gas configuration, which means they have 8 valence electrons, right? That's why it's called the octet rule. Think of octagon. It's a shape with 8 sides. Octet rule means it is going to gain or lose electrons or share electrons to have 8 valence electrons. The exception will be hydrogen and helium, which are happy with only 2 valence electrons, because only 2 valence electrons fit in that 1s sublevel, remember. Now, ionic bond, it's resulting from the transfer of electrons. That's what I was saying up here. It's not a sharing of electrons. It is a transfer, and you're going to hear me say that a lot on this video. And the formula unit is how we actually write ionic compounds. Now, this is the simplest ratio of ions involved in that bond. And we have an example that I'll show you when we get over there. Now, the last thing is polyatomic ion. We won't talk a ton about this today, but it is a group of atoms with a net charge. So not just one atom with a charge, like Br2- or Ba2+, but it's actually a group that has an overall charge. The exception being ammonium, they're usually cations. So they're usually anions. They're usually negatively charged, with the exception of ammonium, which is the positively charged polyatomic. Notice that this is N bonded with 4 H's, and it has a positive charge. That's a charge for the whole NH4, not for just the 4, or not for just that H. Okay. Now, some things to know about ionic bonds are that they are held together, or ionic compounds are held together by the electrostatic attraction. Again, that's just the negative attracting the positive of cations and anions. The metal is going to be the one giving away its electrons. The non-metal, or the anion, is going to be the one taking the electrons, all right? So it's a give and take relationship here. And then when we write the formula unit and the name both for ionic compounds, the metal always comes first, okay? So in CaCl2, Ca is the metal, Cl2 is a non-metal. We would never write Cl2Ca. It's always metal first. Likewise with naming, this would be called calcium chloride, not chloride calcium. Right, so remember the metal cation maintains its name, calcium, and the ending of the anion changes to ide. Again, we'll see that in the next video. And then here's the example of the formula unit that I was going to show you, the simplest ratio of ions involved in a chemical, or in an ionic bond. Fe2O3, you can't simplify 2 and 3 anymore. You can simplify 4 and 6, right, but not 2 and 3, right? So the simplest ratio, 2 iron atoms and 3 oxygen atoms. That subscript indicates how many of each atom there is. Fe2 means 2 iron. O3 means 3 oxygen. Pretty simple enough, hopefully. So now we can get into the fun stuff. So this is actually how we can represent ionic bonds using things that we've just learned. So using electron configuration and Lewis electron dot structures. The how-to for both of these is very, very similar, almost identical, except that one uses electron configurations, one uses Lewis electron dot structures. So the first thing is you're going to write for electron configurations, write the electron configuration for the atoms, then use arrows to transfer those electrons. Let's start there. So here I've already written out the electron configurations for Mg and O. We want to see what kind of bond forms between Mg and O. So the electron, I'm using abbreviated, and you should too for these, otherwise it gets to be very cumbersome. The abbreviated electron configuration for magnesium is neon, followed by 3s2. For oxygen, it's helium, that's the closest noble gas but lighter, 2s2, 2p4. All right, so now that's the electron configuration for the atoms. We want to show arrows to transfer the electrons. Well, magnesium only has 2 electrons to work with in its outer valence shell. Oxygen has 6. Now, is it going to be easier for magnesium to give up 2 or to gain 6 to be like a noble gas? Obviously, give up 2. Is it easier for oxygen to take 2 or to give up 6? Well, 2 is less, so it's going to be easier to take 2. So these 2 electrons from the metal, remember the metal is the one giving the electrons, are going to come down here to oxygen. One of the electrons is going to go here. Now it's at 2p5. So another one of the electrons is going to come here. Now it's technically at 2p6. So we can represent that over here. Magnesium lost 2 electrons, so now it's Mg2+, with the configuration of just Ne, because it's lost these 3s electrons. Oxygen, however, gained 2 electrons. So it's now He2s2, 2p6. Okay, so not 4, but 6, because it gained those 2 electrons from magnesium. And the formula unit for this then is, we have 1 magnesium and 1 oxygen, so it's MgO. That's the formula unit. Let's try another one. Oh, write the new configuration for the ions. Sorry, I forgot to mention that. That's what we did here. The new configuration for the ions and the formula unit up in the corner. So let's do another one. Calcium has an abbreviated configuration of Ar4s2, and chlorine has a configuration of Ne3s2 3p5. You can kind of ignore this one for a second, and you'll see why it's there. Because argon, the metal, is going to give up its electrons. So I'm going to circle the 2. Now it can only give 1 electron to chlorine before chlorine has a full octet. So we need another chlorine to come in for that other electron to go to. All right? So we then have calcium, which again gave up 2 electrons, so calcium with a 2+ charge, and its new electron configuration for the ion, is just argon, because it lost these 4s2 electrons, so just argon. Chlorine, however, has the same configuration, except each one of these chlorines gained an electron. So now it's neon 3s2 3p6, right? 5 plus 1 is 6, and we have 2 of those, right? You don't have to write both over again, just write a 2 in front of there. All right, now the new formula unit here, we have 1 calcium, 2 chloride, so CaCl2, 1 calcium, 2 chlorines, or chloride ions, okay? The Lewis electron dot structure is going to be a little bit different, but not much. The only difference is, instead of writing the electron configuration for the atom and the ion, you're going to write the Lewis dot structure for the atom and the ion, okay? So let's try it out. I've already done the Lewis dot structures for magnesium and oxygen. Remember, look on the periodic table. See, magnesium will have 2 valence electrons, and oxygen will have 6 valence electrons. So, magnesium needs to give up its electrons to oxygen. One of the electrons will come here because there's a space for it. There's also a space for an electron down here, so the other electron will come in there. Okay, that's a transfer of electrons. Show arrows to transfer electrons. Now we're going to draw the Lewis dot structures for the ions. Well, magnesium just lost its 2 valence electrons, so it doesn't have any. It does, however, have a charge. It lost 2 electrons, so it has a 2+ charge. Oxygen, on the other hand, gained 2 electrons, so now it has 8 electrons around it, and also a charge, 2-. Okay? And again, the formula unit is going to be the same as we have up here, because we have 1 magnesium and 1 oxygen. So MgO. Okay? Now down here, one more time, calcium has 2 valence electrons. Chlorine, okay, calcium right here, 2 valence electrons. Chlorine is a halogen with 7 valence electrons in that 17th family. So calcium is going to give 1 of its electrons to chlorine because chlorine has room for 1. But chlorine doesn't have any more room for any others. However, calcium still has 1 to give. So we're going to see another chlorine is going to come in, and that's where this electron is going to go, all right? So we're going to show the new configuration. Calcium just lost its 2 electrons, so it has a 2+ charge and no electrons around it, no valence electrons at least. And chlorine just gained 1 electron. See how this 1 electron went to chlorine? So it has a full octet and a 1- charge. But how many chlorines do we have? 1, 2, so we put a 2 here. And again, 1 Ca, 2 Cl's makes CaCl2. And that's it for ionic bonding.